Hi, welcome back to the lecture series on abstract measure theory with course code MTH701 and course code MMTE305. Now, in this video lecture, we will discuss indefinite integral and absolutely continuous function. Indefinite integral and absolutely continuous functions. Absolutely continuous functions. Before discussing this, I want to recall one of our theorem which we have discussed in a previous lecture, but we didn't completely complete the proof of that theorem. So I want to discuss that theorem here again. First of all, I will write down the statement of that theorem. The statement is, let the function f be continuous. Let the function f be continuous on closed and bounded interval a b. Then f is absolutely continuous if and only if then f is absolutely continuous. Then f is absolutely continuous if and only if the family of divided differences, the family of divided difference functions, divided difference functions, this one, this h is here positive number 0 less than h and s are equal to 1, is uniformly integrable, is uniformly integrable. Okay, in this theorem we have seen that this if this collection of the divided difference function is uniformly integrable, then f is absolutely continuous. And also we have seen that if f is absolutely continuous function, then this divided difference is uniformly integrable, but we have proved that converse only for case 1, where we have assumed that the set E is the finite intersection of open intervals. Okay, so the converse, assume that f is absolutely continuous, assume that f is absolutely continuous, assume that f is absolutely continuous, assume that the function f is absolutely continuous, and we need to show that this collection is the collection of divided difference function is uniformly integrable. That means we show that for all epsilon positive there is a delta positive, such that integral over a, here we can assume that this f is also continuous, absolutely continuous. So we can assume that we can assume that this f is increasing. Okay, increasing. We show that for each epsilon positive there is delta positive, such that integral of divided difference function is less than epsilon by 2, or I can write epsilon also, or epsilon by 2, if Lebesgue measure of E is less than delta, where this E is measurable subset of EB. So in that theorem we have seen this for the set E, where E is the finite intersection of open intervals. Okay, so if E is equal to union ck dk, k runs from 1 to n, where these they are disjoint also, ci di intersection cj dj is equal to the empty set. Then we have seen that then this integral of the divided difference function over this e is less than epsilon by 2 if Lebesgue measure of e is less than delta. This we have seen in case 1, if e is the disjoint union of open intervals. Now we prove the theorem for the case if e is an open set. So case second actually. So in case 1 we have done in our previous lecture. Now we have case 2. If E is an open set, then E is the disjoint union of open intervals. I runs from 1 to infinity, where they are disjoint. And this II is the open interval, AI comma BI. They are all bound open intervals. Every open set can be written as countable disjoint union of open intervals. Okay. So let's define J1 is equal to I1, and in general let's define Jn is equal to union I runs from 1 to n. Then this Jn, they are all disjoint, so each Jn is the disjoint union of open intervals, and for each Jn the result is true, and then this Jn is also monotonic increasing, and this divided difference of the function f over the interval Jn, okay, is less than epsilon by 2 if Lebesgue measure of Jn is less than delta by case 1. Okay. So we assume that Lebesgue measure of E is less than delta, and we will show that integral over E of the divided difference function is less than epsilon by 2. Actually, we need to prove that this expression is true for any open set E. So it's true for these sets Jn, where Jn is the finite disjoint union of open intervals. So now assume that Lebesgue measure of E is less than delta. This implies Lebesgue measure of what's E? E is the union of Jn's, and runs from 1 to infinity. You can easily verify it. It's actually union of I's. I runs from 1 to infinity, but that's union is same as this one, is less than delta, which implies Lebesgue measure of Jn is less than delta for all n greater or equal to 1. So which implies that integral over divided difference of f over Jn is less than epsilon by 2 for all n greater or equal to 1, letting n approaching to infinity. This implies limit n approach to infinity integral over Jn divided difference of f, sorry it's h here, then f is here, is less than epsilon, is less or equal to epsilon by 2. But this limit is same as the integral over E, because limit of Jn, because this Jn, if n is approaching to infinity, it will be the set E. So this is here is less or equal to epsilon by 2, which is less than epsilon. So therefore the result is true for the set E, where E is an open set. And finally case third is if E is a G delta set, then in that case then what's E? G delta means E is equal to the intersection, it's a countable intersection of, it's equal to OI, I runs from 1 to infinity, where OI's are open set. That's the definition of G delta set. G delta set means which is countable intersection of open sets. Okay. So let's define Vn, which is equal to intersection of OI. I runs from 1 to n. Then this Vn is an open set, because it is a finite intersection of open sets, is an open set, and this is also decreasing sequence v1 v2. So you can see this Vn plus 1 is subset of Vn for all n greater or equal to 1. You can easily verify this. V2 is subset of V1 because V2 is the intersection of two open sets and V1 is just over. Similarly, V3 is the intersection of three open sets. So that means this is a decreasing sequence of open sets. It's a decreasing sequence of open sets. Okay, that's so that means and also this E is the intersection of OI. It's same as the intersection of Vn's. Both the intersections are same. So also this E, which is actually equal to intersection OI, I runs from 1 to infinity. It is same as the intersection Vn, n runs from 1 to infinity. N runs from 1 to infinity, where Vn is an open set. Okay. Now we have this integral of divided difference of f over the set Vn is less than epsilon if Lebesgue measure of Vn is less than delta, because this expression is true for open sets. This is true for all n greater or equal to 1. For all n greater or equal to 1. So if Lebesgue measure of Vn is less than delta, that means Lebesgue measure of V must be less than delta. So I want to prove this result for and you can see this Vn is a decreasing sequence. It decreases to E. So if I apply the limit here, this means that the integral over Vn of the divided difference function f is less than epsilon. This is less than epsilon over Vn. Okay. So and this is actually the non-negative function. You can say so it is also true for if Lebesgue measure of Vn is less than delta. It means that Lebesgue measure of I want to prove this for G delta set, actually for G delta, for the set E, which is G delta set. Okay, so this implies so we have this, actually we have given this integral of divided difference function f over Vn is less than epsilon if Lebesgue measure of Vn is less than delta. So this is true for each n greater or equal to 1. So let's apply the limit throughout. So this means it's Vn here. Okay. So we can apply the limit throughout here. It's Vn. So that means limit and approach to infinity, or here I can write epsilon by 2 also. The previous page as well. Let me write here epsilon by 2 because epsilon is any positive number, no problem. It's an integral over Vn of divided difference h of f is less or equal to epsilon by 2 if Lebesgue measure of Vn is less than delta. This is true for all n greater or equal to 1 here. So that means integral over E, because this limit of Vn is actually E, you can easily verify it, it is not too difficult, is less than epsilon if Lebesgue measure of Vn is less than delta for all n greater or equal to 1. So let's apply the limit now here. So this gives integral over E of divided difference function is less than epsilon if Lebesgue measure of E is less than delta. Okay, because this one is true for each n letting n approaching to infinity, or you can say this Lebesgue, or you can simply write Lebesgue measure of E is less or equal to Lebesgue measure of En, which is less than Lebesgue measure of, which is less than delta. That's it. So that proves the theorem for G delta set. Now let E be, that's the last case, any measurable set. Then there exists a G delta set, then there exists a G delta set which we denote by G, such that Lebesgue measure of G minus E is equal to 0, and this E, it is subset of G. This is very simple. Okay, can easily find. For any measurable set E, we can find a G delta set such that Lebesgue measure of G minus E is equal to 0, and this G delta set, it contains E. Now let's try to find the integral over E, where E is now any measurable set. It is same as integral over this is same as integral over E. This is equal to 0. Okay, this is equal to 0. This is same as integral over E divided difference of fh plus integral over can write here G minus C, because that's equal to 0. This is equal to this is integral over E. I need to show that this is less than epsilon if Lebesgue measure of E is less than delta, but Lebesgue measure of E is same as let me do this now. Since result is true for G delta set, so I have to apply that case here. G is a G delta set, so I will apply that the third case actually. So now this integral over G of divided difference f less than epsilon if Lebesgue measure of G is less than delta. This is done. Okay, and here I want to prove this result for now I want to prove this result for the set E actually. As soon as E, G is subset of E, not E is subset of G, so Lebesgue measure of E is so here you can say this integral over G is same as integral over E actually. You can say this because both are the finite measures, and Lebesgue measure of G is same as Lebesgue measure of E. Yes, this is Lebesgue measure this is over E now, because integral over E is same as integral over G. They are actually equal sets here. Less than epsilon if Lebesgue measure of G, Lebesgue measure of E, which is same as Lebesgue measure of G, that's less than delta. Why this Lebesgue measure is same? Because we are given that reason is Lebesgue measure of G minus E is equal to 0, which implies Lebesgue measure of G minus Lebesgue measure of E is equal to 0. So that means Lebesgue measure of G is equal to Lebesgue measure of E. So these Lebesgue measures are same. So that means integral over E is same as integral over G actually, because they have same Lebesgue measures. And this you can easily verify. This is not too difficult. Okay, next. So that proves our theorem completely. Okay. Now next we discuss our topic here, that's the indefinite integral and absolutely continuous functions. Okay. So let's discuss our topic now. Indefinite integral and absolutely continuous. Indefinite integral and absolutely continuous functions. Indefinite integral and absolutely continuous functions. Okay, this is our topic here. We recall that this is already done in your basic course. We recall that in Riemann integration, we recall that a function f defined on closed and bounded interval a b is the indefinite integral of g over ab provided that g is integrable, provided g is Lebesgue integrable, g is, as in case of Riemann integration, provided g is Lebesgue integrable, but here we have Lebesgue integration. Okay, g is Lebesgue integrable over ab and our f is equal to f of a plus integral a to x g for all x belongs to the interval a b. So we say that a function f is the indefinite integral of the function g, provided that g is Lebesgue integrable and f of x equal to f of a plus a to x g, integral a to x. This is Lebesgue integral here. Okay. Now we do our theorem here. A function f on closed and bounded interval ab is absolutely continuous if and only if it is indefinite integral, if and only if it is an indefinite integral. It is an indefinite integral over ab Proof. First we assume that f is absolutely continuous function. Suppose f is absolutely continuous on AB. So then f is absolutely continuous on any subinterval. Then f is absolutely continuous on ax for all x belongs to the interval a b, and therefore therefore integral a to x f dash is equal to f of x minus f of a. This is we have done. Whenever f is absolutely continuous over the interval a b, then integral of f dash over a b is equal to f of b minus f of a. And here the function f is absolutely continuous over the interval ax. Therefore integral a to x f dash is equal to fx minus f a, which implies that fx is equal to f of a plus a to x f dash. So that means this f is indefinite integral of f dash, because this f dash is integral. This is already done. Whenever f is absolutely continuous, then f dash exists almost everywhere, and it's also integrable. So therefore f is indefinite integral. Indefinite integral of f dash. Integral of f dash. Now conversely assume that assume that f is indefinite integral of g over ab. Then g is integrable, Lebesgue integrable. Then g is Lebesgue integrable over ab by definition, and this f of x is equal to f of a plus integral a to x g plus integral a to x g. We show that f is absolutely continuous. We show that f is absolutely continuous. F is absolutely on the interval a b. Okay, for this let's take any finite disjoint sequence of intervals a b. So let's take this let a this is the sequence of open intervals which is disjoint. It's finite sequence actually. B a finite disjoint collection in AB, in collection of open intervals, okay, in AB. And if we define this set, if we define A is equal to union AK BK, K runs from 1 to n, then we can see this, then summation. Can easily verify these things. They are very simple. Mod of f of bk minus f of ak. It's like f of x minus f of a. Okay, but here what's f of x minus f of a here? You can see here f of x minus f of a is equal to a to xg. A to x g. Okay, this is given here. F of x minus f of a is equal to a to integral a to x g. Okay, we apply this one here. This is equal to summation k runs from 1 to n. This f of bk minus f of ak So this one it's equal to the integral, its mod obviously, because the mod is here, it's equal to the integral ak to bk, f dash, not f, it is g. Okay, this, so this is vertical, this is mod actually, this one, so and this is lesser equal to summation by, I can apply this by, say, star. Let me write this as star. Okay, by star. K runs from 1 to n, integral ak to bk mod of g, and that's equal to this, because this is the set E whole, it is equal to integral over E mod of g, So let's write this as double star. Okay, so this summation is less or equal to this. Okay, so now let epsilon be any positive number. Since mod of g is integrable, so therefore there is delta positive, therefore there, for integral function, there exists delta positive such that integral of mod of g is less than epsilon if Lebesgue measure of E is less than delta. If Lebesgue measure of E is less than delta, while E is measurable, So therefore, since our E is measurable, here you can see it's this E is measurable because E is the union of the open intervals. So E is measurable. So therefore, if Lebesgue measure of, if in double star, you can see, therefore if in double star Lebesgue measure of E is less than delta, then what is the Lebesgue measure? Then this summation bk minus ak, because this is the E is the set of the union of those intervals, they are disjoint, is less than delta, and this implies because this is same as Lebesgue measure of E actually. Lebesgue measure of E is equal to this, which is less than delta. Then this implies integral. This implies not integral. I will write the summation here. That's equal to integral. This implies summation k runs from 1 to n f of bk minus f of ak, which we have verified it's less or equal to integral over E mod of g, and that's less than epsilon. You can say it's by triple star. Let me write this expression as triple star. Okay, this one. Whenever E is any measurable set with the Lebesgue measure of E is less than delta, then integral over E of mod of g is less than epsilon. But integral over E mod of g is equal to that sum. It's equal to this sum actually. It's equal to this sum. So this sum is less. It's less or equal to that one. That integral of g, and integral of g is less than epsilon whenever Lebesgue measure of E is less than delta. So that means whenever the sum of the lengths of the interval is less than delta, then this oscillation is less than epsilon, which implies f is absolutely continuous. F is absolutely continuous. So that proves this theorem completely. Next, we prove one more theorem. Theorem is let the function f be monotone. Let the function f be monotone on a closed and boundary interval a b, then f is absolutely continuous. So this is very interesting result. For monotone function, this result is very interesting. Then f is absolutely continuous. F is absolutely continuous if and only if integral a to b f dash is equal to f of b minus f of a. Proof. If f is absolutely continuous, if f is absolutely continuous, then this integral is always equal to this without using that f is monotone. Whether f is monotone or not, this is always true. But whenever f is absolutely continuous, this is always true. Then integral a to b f dash is equal to f of b minus f of a, without assuming that f is monotone. But here our function f is monotone, okay? And that monotone property of f we will use in the converse actually, not in this part. If f is absolutely continuous, then this integral is equal to f of b minus f of a. Integral a to b f dash is always equal to f of b minus. This is already done in our one of our theorem, okay? Now we prove the converse. Conversely, assume that a to b f dash is equal to f of b minus f of a, okay? So name it first, okay? Since f is monotone on AB, therefore it is monotone on a to x and x to b for all x belongs to the interval AB, because they are sub-intervals actually, sub-intervals of AB. It's monotone on whole interval, therefore this f is monotone on this interval as well as on this interval. So whenever it's monotone on this interval, then we have done, if f is monotone on AB, then integral a to b f dash is less or equal to f of b minus f of a. So then integral a to b f dash is less or equal, sorry, it's a to x here now, because it's monotonic increasing on a to x, it's less or equal to f of x minus f of a, and integral x to b f dash is less or equal to f of b minus f of x. So this gives integral a to x f dash minus times f of x minus f of a, this outside of this integral, this is less or equal to 0, and second one, this integral x to b f dash minus f of b minus f of x is less or equal to 0. Now from 1, you can see from this one, okay? Now from 1 is this equation here, this name it this one, it's 2 whole, okay? 2. From 1 we have 0 is equal to a to b f dash minus f of b minus f of a, okay? This is equal to a to b f dash minus f of b, okay, f of b minus f of x plus f of x minus f of a. This I can do, okay? Now I will write it as a to b f dash, I will first write this f of b minus f of x Okay, oh sorry, let me write one more step here first. It's equal to this one, this integral. It's equal to integral a to x f dash plus integral x to b f dash minus this whole f of b minus f of x plus f of x minus f of a. Okay, now I will club these two terms, a to b f dash and this one f of x minus f of b, and then I will club these two, x to b f dash minus this. Okay, this is equal to a to x f dash, then I will write this one minus times this f of x minus f of a. Okay, minus times f of this, on this side it's equal to 0. Okay, it's all equal to 0, minus f of a, then plus I will write this one a to x, sorry, it's not a to x now, it's now x to b. Okay, x to b f dash minus f of b minus f of x. Okay, so this sum is 0, but both the terms are less or equal to 0 by 2. Both the terms are less or equal to 0. Both these terms, they are less or equal to 0. So it means that both must be equal to 0, because if one of them is strictly less than 0 and second is less or equal to 0, then sum will be negative. But sum is equal to 0, so this implies a to x f dash minus f of x minus f of a must be equal to 0, and this one is also equal to 0 by second. So this gives can transfer this fx on this side. This gives f of x equal to f of a plus a to x f dash, so which means that f is indefinite integral of f dash, which means that f is absolutely continuous by previous theorem. This implies f is indefinite integral of f dash, and hence by previous theorem f is absolutely continuous. F is absolutely continuous. Okay, so now the next theorem is let f be integrable. Let f be integrable over closed and bounded interval a b, then this holds. Then f of x equal to 0 almost everywhere on a b if and only if integral from x1 to x2 of f equal to 0 for any subopen interval of the closed interval a b. Okay, this is again the proof one way it's trivial. If it's 0 almost everywhere, then integral is 0 throughout. Okay, if f of x equal to 0 almost everywhere, so this implies integral over any subinterval of f equal to 0 for all x1 x2 subset of the closed interval ab. The converse is very important. Okay, conversely assume that assume that the integral over any subinterval of f is 0 for any subinterval of a b. Okay, we show that f equal to 0 almost everywhere. For this we first show that we first verify that integral over E of f is equal to 0 while E is any measurable subset, where E is any measurable subset of A, B. Okay, we prove this first. So E is any measurable subset. First we prove it for open set. Okay, case 1. If E is open, open set, then E can be written as countable disjoint union of open intervals, where ion is a disjoint sequence of open intervals. It is a disjoint sequence of bounded open intervals. Now let's try to find integral over it of the function f. It's equal to integral over this union and runs from 1 to infinity of f, and that's simple, it's summation, and runs from 1 to infinity integral over I n f. But this one is equal to 0 because integral over any subinterval is equal to 0, so it's equal to 0. Now is any measurable set. Case second. A is a measurable set. Then there exists a G delta set, say G, such that E is subset of G and Lebesgue measure of E is same as Lebesgue measure of G, because they are all finite. So actually Lebesgue measure of G minus E is 0, which means Lebesgue measure of G is same as Lebesgue measure of E. So also now this G is a G delta set. We have, what's G? G is the intersection of open sets. O and N runs from 1 to infinity, and O n is open set. And for open sets result is true. Now this integral over O n of f is equal to 0 for all n greater or equal to 1. And this is actually decreasing. O n is open, and O n plus 1, it's explained in one of our previous theorem. We can take this as a decreasing sequence of open sets. Okay, so integral over this O n is equal to 0 for all n greater or equal to 1. So by taking the limit, so this implies limit n approach to infinity integral over O n of f equal to 0. This implies integral over G delta set of f is equal to 0. Now what is integral over E of f? It is same as integral over G of f. They are same, but this one is equal to 0. Okay, so integral over any measurable set is equal to 0. If integral over any interval, any subinterval of AB is equal to 0, then integral over any measurable subset of AB is equal to 0. This we have proved. Now let's define these sets. Define E plus, which is equal to the set X, such that those points in AB where the function is positive, and E minus those points in AB such that the function is negative, then both e plus and e minus are measurable, then both, because f is a measurable function, both e plus and e minus are measurable subsets of a b. So therefore integral over e plus of f is equal to 0 and integral over e minus of f is equal to 0. Okay, this implies but integral over e plus of f means that integral from a to b of the function f plus the positive part is equal to 0, and integral over e minus means that it means that integral over a to b of f minus is equal to 0. Of f minus is equal to 0. Now this you can easily verify that because the function is negative on this range, so therefore it's equal to f minus on this range. It's equal to f minus. Okay, they are same. But both the functions, they are not non-negative functions actually, since I can write it as this implies integral over a to b f plus is equal to 0 and integral over a to b minus times f minus is equal to 0. So they are both positive functions and their integrals are equal to 0. This means f plus is equal to 0 almost everywhere and f minus is equal to 0 almost everywhere. So that means that their sum is equal to 0 almost everywhere, which is equal to f plus minus f minus is equal to 0 almost everywhere. Is equal to 0 almost everywhere. So next we have the last theorem of this section, which is let f be integrable over, let f be integrable over the closed and bounded interval a b, then f is integrable. Okay, then d by dx of integral a to x f is equal to f of x almost everywhere. Okay, so I will leave this proof as an exercise for you, or if you want to see the proof, it's theorem number 14. Theorem 14, page number is 126. Okay, on H.L. Royden. If you want to see the proof, so it easily follows from previous terms. So this completes the video lecture. In the next lecture we will discuss Cantor set and Cantor-Lebesgue function, and we will see that the Cantor-Lebesgue function is not absolutely continuous. Okay, Cantor-Lebesgue function is not absolutely continuous, but that function is monotonic increasing and also continuous, but not absolutely continuous. Okay, that we will do in